So continuing with analyzing two variable relationships or bivariate data, we talked about in the first lesson about how we can show a two variable relationship graphically using a scatter plot. And scatter plots have different characteristics, 4 different characteristics we can describe. And we did talk a little bit about a line that we could put on the scatter plot that would best describe the relationship. That's really what we're going to focus on. We didn't go too much into it, so we're going to focus on that. And it is also called the line of best fit. Okay, bless you. We're going to focus on that today. So here's an example, because we usually start with this example. So low-income students tend to have lower attendance rates and lower math test scores. So a study was done, or a random sample of students in Texas was collected, and their percent attendance was recorded along with their raw score, that's not a percentage score, how they did on an algebra state exam. So probably we could see, actually, let's answer this question first. What's the explanatory variable? Percent attended. And the response? That's 4, right? Because the percent attendance is going to be used to predict the test score if there is such a relationship. Okay. And we can see that actually, just remember the explanatory variable is always the X, which means in a table it's always the first column, and on the graph it's always the horizontal axis. Whereas the response variable is the Y, so in a table it's the second column, and on a graph it's the Y axis. Okay, so we can see some kind of relationship going on here. What would you say? Do you see a relationship? So what would you say right now about this? Yeah, if your percent attendance is high, or if your percent attendance is really low, it looks like your test score is going to be really low, right? Well, that's great, but we want to use this information to predict other test scores. Like right now, we only have what, 4, 8, 10 students. Okay, we want to use this sample to predict test scores for, say, all students in Texas, or all students at least in that county or city or wherever it is. So with that, we want to put a line in that is called a regression line, or a line of best fit. And that line means we can make an equation of that line, which means we can do math to make predictions. Okay. How do we get this regression line? Well, first of all, we always look at the residuals between the actual line we put in and each data value. We're going to talk about residuals in more detail later, but a residual is the vertical distance or difference between an actual value and the value that's going to be predicted by the regression line. So for example, if we put in, and we're going to do a regression line for this, but let's just say I draw one in. And I'm going to draw one so it looks like that. Okay. Well, the way that I've drawn it, we can see a bunch of vertical distances. Like there's a distance or a difference between this actual value and the regression line, which would be positive because it's above. This one would be a negative difference because it's below. So all of these red ones that I'm drawing, the differences between the actual value and the regression line, those are all the residuals. Okay, that's the difference. The last, or the first and the last point, so the point to the furthest left and the point to the furthest right, would have a zero residual, because that's just the way I drew it. Okay, but we're going to get into more residual. We're going to get more into residuals later on. I only want you to be familiar with that term when we talk about the regression. Yeah.
Standard.
Kind of, yes. And we actually do squaring is involved. Yes, standard deviation we use for one variable data. Residuals is what we can use for two variable data. Good. So how do we put the line in? Like how do we know where to put the line? Well, it depends on how the dots are formed. Okay. We don't want to minimize the, like obviously we want the dots, the data value dots to be as close to the line as possible, right? That means we've got a good line, okay? But how do we do that? Well, we actually don't find just the difference in residuals. We find the difference in the residuals squared, right? The difference in residuals would, we could draw multiple lines that would have the same difference in residuals, so it's useless. So we need something that's going to separate it. So what we want to do is we want to find the difference of all the data value points from the line, square them, add them together, and we want that sum to be as small as possible. The smaller it is, the better. So for example, here, we've got some points in graph A, where we've drawn a regression line that goes through the middle point. It's 2 above on the bottom point and 2 below on, or sorry, it's 2 above on the point to the left, 2 below on the point to the right. Okay. If I find the square of the residuals, well, this is a difference of 2, 2 squared is 4. This is no difference, so 0 squared is 0. This is 2 below, but remember when I do negative 2 squared, I get 4. So the sum here would be 8. Okay. Whereas if I just tilted it a bit so that it went through all 3, okay, I can see that I can actually draw a line through all 3. And notice what the sum of the residual squared is now. It's 0. So obviously, line B is a better fit. Because the sum of the residuals squared is as small as we can get, or as small as possible. We can't get a sum less than 0. Because remember, when we square them, everything becomes positive. So you can see here on the next scatter plot, this is the actual residual line. I was close, but a little bit off. Or sorry, the least squares regression line, not the residual. So the way, if we fit in the line like this, the sum of the squares of the residuals will be as small as possible. Okay. So this is something that you should be familiar with. the sum of the squares of the residuals. You definitely want to be familiar with that definition. Why do we call it a least squares? Because the sum of the squares of the residuals is minimized as small as possible. Okay. Okay, so we've got a line. We put the line in. What do we do with this line? Well, we want to use it to make predictions. Okay. And in order to make predictions, we need to quantify it. And how do we quantify a line? Well, you guys have learned y equals mx plus b. Right? That's the equation of any line, where m represents the slope of the line, it goes in front of the x-coordinate, b is the number after, and that represents the y-intercept of the line. Unfortunately, in stats, it's a slightly different equation, although it has the same meaning. We actually write, but we use slightly different notation too. Because remember, we're making a prediction line. So it's not just the y value, it's the predicted y value. And we call that y with a little roof over it, y hat. Instead of writing the y-intercept at the end, we write it at the beginning, we call it a. So when you guys learned y equals mx plus b, b was the y-intercept. But with stats and linear regression equation, the y-intercept is a and it comes first. And for the number that's in front of the x, well, we learned m when we did it using y equals mx plus b. It comes at the end in the stats regression equation, and we call it b. That represents the slope, which makes sense. Why did I call it y-interest? Did I call it what? What's wrong with me today? Y-interest. Y-interest. Okay. So here, not only have we put the regression line on the scatter plot, but we've managed to determine its equation. Okay. So the equation is the predicted y, or y hat, is negative 7.69 plus 0.57 times the percent attendance. So if we want to get the predicted test score, we do this calculation, whatever the percent attendance we have is. Something that we obviously do in stats more than we do like pre-calculus, we do interpretation. So not only do you need to be able to identify the y-intercept and slope of a linear regression line, you need to explain it in context. Okay? And this is sort of the stem that you use. You say for every 1 unit increase in the explanatory variable, our model predicts an average increase or decrease of whatever the slope is in the response variable. So in this specific example, how would we interpret the slope? We would say for every 1, what's the units First of all, what's the explanatory variable? Percent attended, so the units is percent. So for every 1% increase in percent attendance, our model predicts, and now we're going to determine whether the slope is positive or negative, see if it increases or decreases. Well, it's positive, so it's going to be an increase. So it predicts an increase in, and now write the slope, 0.57 in raw test score. If it was negative, it would be a decrease. Like if for some reason, if percent attendance went up, the test scores went down, we would say decrease instead of increase. Wow. Maybe I could finish the sentence. Maybe I could finish the word. Predicts an increase of 0.57 in raw test score. And what's the y-intercept? Well, it's when x is 0, or it's when the explanatory variable is 0. Okay, so when the explanatory variable is 0 units, what's the response variable amount? So in our example, when percent attendance is 0, our model predicts the test score would be what? What would the test score be if? Right. Negative 7.69. One additional question you can ask about the y-intercept is, does it have meaning? Does it actually have meaning in this context? So what we're saying is that if you didn't go to school at all, your score would be in the negatives. Does that make sense? No, you can't have a negative score. So in this context, no, you can't have a negative score. Sometimes the y-intercept will have meaning, sometimes it won't. Okay? In this case, it doesn't. Yeah, that's right.
If it were to be above like,
Then you could say it has meaning. Like if it was, say, 2 or 3 or something like that, you could say, well, maybe the student guessed at something and got something. But because it's negative, it has no meaning. And of course, what's the other thing we can do with an equation? We can actually make predictions. So this is just plugging in and calculating. That's all this is. So the superintendent of this district asks, if a student meets our minimum attendance goal of 87%, what would be their predicted test score? Okay. And notice you don't plug percent in as a decimal, because if we look at the beginning, the regression line was based on percent attendance. The percentage is not decimals. So don't change the decimal. So all you have to do here is we want to find the predicted test score. when given the equation negative 7.69 plus 0.57x, x is 87. So it's just a straight calculation. And when you calculate that, you're going to get about 41.9 points. So the minimum attendance percent predicts score of 41.9. Okay. So really what I want you to get out of this thing is the definition, the meaning of a least squares regression line, what the form it takes, how we can analyze the slope and y-intercept in it, and how we can do some calculations with it. Okay? Just a quick discussion. So this is what we saw. Or sorry, no, that's not what we saw. So initiatives were taken to try and get chronically absent students to school. Okay, so they had attendance managers or coordinators. They were using Uber to bring students to school, okay, to try and increase attendance. So this happened over time. They managed to increase attendance. And yet when it came to the test scores, this is what happened. Why? What do you think? Just sort of think common sense. The attendance went up, okay?
For example, like, which is really good.
Okay.
Like last time we did our discussion, we talked about like sharks and ice cream, right?
Yeah.
And how the two arts, of course, one increases with the other, but they aren't directly associated with each other. Attendance level, sure, and you see.
Right, so this seems to suggest that attendance didn't affect the test scores. Okay, which seems to suggest that maybe there's some other factors at play. Okay, don't think so much about what's happening in school. Okay, these are low-income students. Okay, from low-income families. What other factors may cause, yeah, not enough resources, right? Especially at home. Maybe there's not the support at home that they're getting, right? Because I mean, parents are working 2-3 jobs. So kids are on their own a lot at home. Which means even though they're going to school, when they come home, they're not doing anything. So they're not learning anything and their test scores aren't going to go up. That's something to sort of keep in mind, especially when we talk about the next unit on how to do experiments and things like that. Because sometimes other factors may come into play that can ruin experiments or ruin studies. Okay.